Okay, hello everyone, welcome back. So in the last set of videos, we saw the definitions of position, velocity, and acceleration for the simple case of a particle moving along a straight line or a rectilinear motion. So there in the previous videos, we saw you can have a reference, and based on that reference along the straight line, you can essentially measure the position using a tape measure. One side could be positive, the other side could be negative. So position could be described using a scalar variable. You had s as position, and then we saw velocity was the rate of change of position, how fast the position is changing. So ds over dt, or we called it also as dot. Similarly, acceleration was the rate of change of velocity, how fast velocity is changing, and that is dv over dt, or we called it v dot, or because v is derivative of position, this becomes second derivative of acceleration becomes second derivative of position. So we had these, and we also saw an expression that was relating positions, velocities, and acceleration to each other without a notion of time in the equation, and that was a ds equals v dv. And with these three, you can see that if you have s, you can take derivative, d over dt, gets you to velocity. You can take another derivative, d over dt, gets you to acceleration. It is also possible to go backward from acceleration to velocity to position using integral. So you can go back here. Instead of taking derivative, you take integral. From integral of acceleration becomes velocity, and integral of velocity gives you position. So let me write it down here, that if you have acceleration, you can take integral acceleration dt, that gives you v, and if you have v, you can take integral, that gives you s. Or if you have the definite integrals, the bounds are given, these integrals can give you change in position or change in velocity. So let me actually write it down. So v2 equals v1 plus integral from t1 to t2 of a dt. Similarly, s2 can be s1 plus integral of t1 to t2 v dt. And this is in the integral form. You can go back from higher order variables to lower order variables. Let's actually take a look at this one too. We have ADS. Well, actually, no, that's fine. You have ADS equals V dV. It doesn't have explicit time in it, but you still have these differential variables, and you can very easily take integral of both sides. So integral of ADS equals V dV. So here no longer the bounds of integral. The integral is on time, but the two integrals, one is on variable s, the other one is on variable v. And you can integrate it from some s1 to s2, and the other integral would be from some v1 to v2. And in this case, this becomes very useful if you know, let me make it a little bigger, give us more space. like that. If your acceleration, you know it somehow as a function of position, and your velocity, you know it. It has to be as a function of. No, you don't need this. You don't need that. V dv. So it is important, if you're going to use this equation, you need to know your acceleration as a function of position, which becomes quite often a case. For instance, when you are looking at a pendulum or a spring is a better example, that you know accelerations, it is related to forces are related to positions, how far this spring is stretched. So you can use such equation to go from, I don't know, one state to another without really knowing how much time has passed. So, okay, I think that is all I have. We can take a look at a bunch of examples of these, how we can use these to find variables, I don't know, positions or velocities if you know accelerations or vice versa in class. But that is all I have for now. And yeah, I leave you with this.